Welcome to the fourth section of the seminar on partial differential equation and applied mathematics. Today we will have two interesting lectures. First, Andrea Mondino, University of Oxford, United Kingdom. Second, Ivone Ribas Trevino, Universidade del Valle da Colômbia. President Andrea Mondino, we invite the Professor Max Souza, da UF, to introduce Ivone Ribas, we invite the Diego Souza, Universidade de Sevilla. Professor Max, now, follow you, please.
Thank you, Rincon. Thank you, Professor Rincon. Yes, it was a pleasure to receive in our seminar today Professor Mondino from the University of Oxford. Professor Mondino is a well-known expert in nonlinear PDEs and applications to optimal transport and PDEs. And he's quite a successful career. Started on the prestigious University of Torino, going through a PhD on Sessão at Neste, and then have been to many places in Zurich and ETH until then went to Warwick, and now it's got his position at the Mathematical Institute at Oxford. So today he's going to talk to us on optimal transport and quantitative geometric inequalities. So Professor Mondino, thank you very much for accepting our invitation. The screen is all yours. Thank you very much.
Thank you very much. Thank you very much for the kind invitation and for the kind presentation. So it's a great pleasure for me to give this talk to this broad audience in South America and Portugal and Spain, all the places that I love to visit. I went in honeymoon in Peru, so it's a place that I have fond memories of it. So, all right. So today I would like to talk about optimal transport and quantitative geometric inequalities. So more precisely, I would like to discuss some recent geometric inequalities in sharp and quantitative form for smooth Riemann manifolds, and the proofs will involve optimal transport tools. And more precisely, I will give a survey of how optimal transport tools that have been developed in non-smooth settings, typically to understand the lower bounds on the Ricci curvature for metric measure spaces, so where the ambient space is non-smooth. Well, these techniques, some of these techniques have been also useful to study, to establish new applications even for smooth Riemann manifolds. So I will present two results. The first one is a quantitative Levi-Gromov isoparametric inequality. This is joint work with Fabio Cavalletti from Sessão and with Francesco Maggi from Texas Austin. And the second result is a quantitative Obata rigidity theorem with Fabio Cavalletti and Daniel Semola, who is a postdoc in Oxford. All right. So let me start with as a warm-up with something that we all know very well, which is the isoparametric problem. So the isoparametric problem is one of the oldest problems in mathematics, which has its roots in myths of more than 2,000 years ago, the famous quintet problem. And the basic question of the problem is the following. We are given a space X and the volume V. And the question is, what is the minimal amount of boundary area which is needed to enclose such a volume V? So what is well known is that if the ambient space is Rn, so is the Euclidean space, then we have the Euclidean isoparametric inequality, which says that given any Borel set E in Rn, then the perimeter of the set, so let's say that this set has a smooth boundary, so the boundary measure of the set is bounded from below by the perimeter or the boundary measure of the round ball in the Euclidean space. And you take the round ball having the same volume as the Borel set E, of course. Okay. So the ball is the optimal shape for the Euclidean isoparametric inequality when you fix the volume. And if your ambient space is the sphere, say the sphere Sn, then you have an analogous statement, which is that given any set E, any Borel set E in the sphere, say with finite perimeter, then the perimeter of E is bounded from below by the perimeter of a metric ball, which is in the sphere is a spherical cup, having the same volume as the set E. Let me stress that in both of the examples, both in the Euclidean isoparametric equality and in the spherical isoparametric equality, the space is fixed, is either the Euclidean space or the sphere. What happens is that such a space contains a model subset, which is a metric ball. And then what we do is we compare the perimeter of any set E with the perimeter of the model subset. Okay, now let me move to the to a more general setting. So now, besides the Euclidean isoparametric equality, one of the most famous isoparametric equalities is the Levi-Gromov one. We say the following. Now we are given an n-dimensional Riemann manifold Mn with Riemann metric G with the Ricci curvature bounded from below by n-1. This means, for the non-expert, this means that the Ricci curvature is a symmetric bilinear form. So it's a 0-2 tensor, symmetric 0-2 tensor, which is diagonalizable with respect to the metric G. This the fact that the Ricci bounded below by n-1 means that all the eigenvalues of the Ricci are bounded below by n-1. So Ricci is a symmetric bilinear form. It is diagonalizable. All the eigenvalues must be at least bigger than n-1. Right? Now, so we have a manifold with Ricci bounded below by n-1, and we take a domain E with the smooth boundary for simplicity, but say fine perimeter set would be enough. And then we want to compare the perimeter of the set E with something with some model subset in some model space. So now the model space is going to be the round sphere of unit radius, and we make this choice because the round sphere of unit radius is the model space for the Ricci curvature equal to n-1. So the sphere has constant sectional curvature equal to 1, and so Ricci curvature constant equal to n-1. So you are saturating the lower bound on the Ricci curvature. And then inside the sphere, we consider the metric ball B having the same renormalized volume as E. So when we have the Euclidean isoparametric equality or the spherical isoparametric equality, we take the ball with the same volume as the set E. Here we need a normalization more. So we are considering the volume of E divided by the total volume of the manifold, and we choose the ball inside the sphere such that the volume of the ball divided by the volume of the sphere is equal to the corresponding thing for the set E. Okay, so we have given such a ball, and then the isoparametric inequality tells that the renormalized perimeter of E is bounded from below by the renormalized perimeter of the ball inside the sphere. Okay, so what is the renormalized perimeter? Means we take the perimeter of E, or say, since E has smooth boundary, say the boundary measure of the boundary of E, we divide it by the total volume of the manifold, and we compare it with the corresponding quantity for the ball. So this is bounded from below by the perimeter of the ball divided by the total volume of the sphere. Okay, this is the famous Levi-Gromov isoparametric equality, which is basically saying that if you have a manifold with Ricci bounded below by n-1, then isoperimetry is at least as strong as in the model space, which is the sphere. Okay, but there is a big difference between the Levi-Gromov isoparametric equality and the Euclidean or the spherical isoparametric equalities, because while in the Euclidean and in the spherical isoparametric equalities the space was fixed, in the Levi-Gromov inequality the space is not fixed. Okay, so what is happening is that any subset in any manifold with Ricci bounded below by n-1 is compared with a model subset, which is spherical cup, a metric ball, inside a model space, and the model space is the n-dimensional sphere. Okay, so we have much more freedom. We are not just moving the subset E, but we are also moving the ambient space. Okay, and the second comment is that the Diagram of inequality is global in the space. In which sense? In the sense that if we change, so in the sense that it does not depend just on E, but also on the complement of E inside M. Because if we change the manifold outside of E, then we may change the volume of M, and notice that the volume of M is appearing as the denominator in this left-hand side. Okay, and we are going to see in a moment this feature of the globality of the theorem of inequality on the whole space. So, in order to simplify the notation, for later on, let me introduce a little bit of names of notation. So, given a Riemann manifold M, we define the isoparametric profile function of the manifold as follows. So we consider the infimum among all the Borel sets having renormalized volume equal to V, where V is a given number between 0 and 1. So we fix V between 0 and 1. Then we consider all the possible Borel sets with renormalized volume equal to V. And then we take the infimum of the perimeter of the renormalized perimeter among all these sets. Okay. All right. Now the theorem of inequality can be stated as follows: given an n-dimensional manifold with h bounded below by n-1, then the isoparametric profile function of the manifold is bounded below by the isoparametric profile function of the round sphere of radius 1. Okay, and this holds for every V, for every renormalized volume between 0 and 1. Okay, so notice that since we are dividing by the volume of the ambient manifold, this parameter V just runs between 0 and 1. 0 corresponds to the empty set, and 1 corresponds to the whole manifold M. All right, and once we introduce this notation, we can, of course, the theorem of inequality, it can be stated in this simplified form, and it is attached to the theorem of inequality. We have a beautiful statement, which is the rigidity statement, which says the following. So if there exists some Borel set E inside M of non-trivial volume, so whose normalized volume is strictly between 0 and 1, and which achieves the equality in the theorem of inequality, so such that the normalized perimeter of E is equal to the isoparametric profile function of the sphere of volume V. Notice that by the theorem of inequality, we know the bigger or equal here. But if we achieve the equality in the inequality, then we have the so-called rigidity. So then the space is very special and the subset is very special. So then the manifold is isometric to a round sphere, okay? And the subset E is isometric to a metric ball. Okay, so this is a very beautiful rigidity statement. And here you can see really the globality of the theorem of inequality, right? Because even if this V is very small, say that V is equal to epsilon, slightly bigger than 0. So even if you find a very, very tiny subset E of a very, very tiny volume epsilon, which achieves equality in the theorem of inequality, then globally your manifold is isometric to the round sphere. Okay, so here you already see that the theorem of inequality is some global information on your manifold. Okay, and the question that I want to address today is about the stability. So the stability is what can we say if the equality is almost attained? So in the rigidity, we study what happens when the equality is attained. And in the stability is what can we say if the equality is almost attained? So, and I like to divide the stability question into two sub-questions corresponding to the rigidity parts 1 and 2. So the first question is, what can we say if on the space? So what can we say on the manifold M if the equality in the theorem of inequality is almost attained? Is it close to a sphere? In which sense? And regarding part 2, so what can we say on the set E? Is it close to a metric ball, and in which sense, in which topology? Okay, so when equality is attained, then the manifold is exactly the sphere. If equality is almost attained, we expect the manifold to resemble the sphere or to have some property of the sphere. And the same for Western. We expect it E to be close to a metric ball or having something common to a metric ball. Okay, so this is the rough idea that I want to investigate in the next few slides. So about question 1, so what can we say on the space if the equality is almost attained? So this is a special case of a beautiful paper by Berarber, Songalò, and Invenciones, who proved the following. So they proved that if you have an n-dimensional manifold with reachable and below by n-1 and with diameter equal to d, recall that from the classical Bondi-Magnus theorem, if a manifold has Ricci bigger than n-1, then the diameter is at most pi. That's because pi is the diameter of the sphere. And here you're saying that the Ricci is bigger than the one of the sphere of radius 1. Then the geodesics are focusing more than in the round sphere, and so the diameter must be smaller than the one of the sphere of radius 1. This is the rough intuition behind this diameter bound. Okay, then under this assumption, reachable below by n-1 and then diameter equal to d, then we can find a lower bound on the ratio between the isoparametric profile function of the manifold and the isoparametric profile function of the sphere for every v. And it is explicit, and you can bound from below by this ratio. So so you are integrating the same function, which is the cosine t to the power n-1, but at the denominator you integrate this function up to d over 2, and at the numerator you integrate it up to pi over 2. Now you recognize that the cosine on this interval is strictly positive, is positive, and all right, the diameter is at most pi, and so you have that this right hand side is always bigger or equal than 1, and is equal to 1 only if the diameter is equal to pi. All right. So if the equality is achieved in the Levigram of inequality, here you see suddenly that the diameter must be equal to pi. Okay. But this is more strong because it also says that if this ratio on the left hand side is close to 1, then also the one in the right hand side must be close to 1, which means that the diameter must be close to pi in a quantitative sense. One can really quantify it. Okay, one can do the computation, and one can check that there exists some constant which depends on the dimension and on the volume, such that if for some v between 0 and 1 the equality in the Levigram inequality is almost achieved, so if this also, so the isoparametric function of the manifold M is bounded from above by the one of the sphere plus delta, this delta is the error that you're doing the rigidity, then your diameter is close to pi in a quantitative sense. So it is close to pi with an error delta to power 1 over n. Okay, and now it is already saying that that the manifold has something close, has some property close to the sphere of radius 1, because the sphere of radius 1 has diameter exactly equal to pi. But there is more. Indeed, by a beautiful result by Chia Colding published in the Annals, what they prove is that if the diameter is close to pi, then the manifold must be close to a spherical suspension. So the spherical suspension must be thought of as a kind of non-smooth analog of the round sphere of radius 1 in the non-smooth setting. Okay, so when you have a smooth manifolds, then the Cheng maximal diameter theorem tells you that the manifold must be isometric to the round sphere of radius 1. But if your manifold has a diameter close to pi, then you may not be close to a sphere of radius 1 in Gromov-Hausdorff sense. You're going to be close to a spherical suspension, which you can think of it of kind of a lemon, okay? A non-smooth analog of a sphere. All right. Okay, so this is about question 1. Now, what about question 2? So question 2 is what can we say on the subset E? Okay, so in order to get a feeling of this problem, let's see what we can say on the subset E when we are dealing with the more classical Euclidean or spherical isoparametric inequalities when the space is fixed. Okay, so when the space is fixed, so let's start with the Euclidean isoparametric inequality. So this is a result by Fusco, Maggi, and Pratelli, which goes under the name of quantitative Euclidean isoparametric inequality. So what they prove is that there exists a constant, which depends just on the dimension, such that for every Borel subset E in Euclidean space, Rn, there exists a round ball optimally centered in Rn with the same volume as the set E, and such that you can bound the volume of the symmetric difference between E and the ball, normalized by the volume of E, by what? By the deficit that you commit in the isoparametric inequality. So on the right-hand side, you have the constant Cn, and then you have the ratio between the volume of the boundary of E divided by the volume of the boundary of the ball minus 1. So to the power 1/2. Okay. So of course, this left-hand side is non-negative. So by the fact that this left-hand side is non-negative, you get that also the right-hand side is non-negative, which means that the perimeter of E is at least the one of the metric ball. So you reobtain the Euclidean isoparametric inequality. But more strongly, you have that if this right-hand side is equal to 0, so if the perimeter of E is equal to the perimeter of the ball, then also the left-hand side must be equal to 0, which means that the symmetric difference between E and a ball must be equal to 0, which means that E must be equal to a ball up to a set of measure 0. So you reobtain also the rigidity. But this statement is even more strong because it is saying that if the right-hand side is close to 0, so if E is almost optimal in the Euclidean isoparametric inequality, then the set E must be close to a metric ball, to a Euclidean ball, up to a set of measure 0, up to a set of small volume in a quantified sense with exactly with this formula. Okay, and this exponent is sharp. Okay, so how they obtain this beautiful result? They basically they consider the proof via symmetrization of the Euclidean isoparametric inequality, say the Steiner symmetrization, and then they basically quantify that. So they basically have a quantitative symmetrization. They quantify the symmetrization proof in the of this inequality. And since it is a beautiful result, there has been various alternative proofs. When you have a good result, it is having more proofs of a result is a symptom that this result is interesting. So there's been more than one proof of this inequality. Another one was obtained using L2 optimal transport using the Brenier map by Figalli, Maggi, and Pratelli in Invenciones. And there's been a third proof of this inequality by Cicalese and Leonardi using a selection principle and regularity theory for minimizers of the perimeter with area, so for isoparametric sets, basically. Okay. All right, so this is in the Euclidean setting. Now, what happens when the ambient space is the sphere? What can we say on the set E if it almost achieves equality when the ambient space is a sphere? Well, this was investigated by Bogelain, Dutar, and Fusco, and what they prove is that basically is the analog of the Euclidean counterpart. So they prove that for every volume V and for every dimension n, there exists a constant with the following property. So for every subset E inside the sphere, having normalized volume equal to V, there exists a metric ball B inside the sphere, having the same volume as E and such that the symmetric difference between E and the ball is bounded from above by the dimensional constant, depending also on V, times, now you have the spherical isoparametric deficit, which is, so you're taking the normalized perimeter of E, and you take out the isoparametric profile function of the sphere. So this is checking how close is E from achieving equality in the spherical isoparametric inequality to power 1/2, and it is saying that if E is almost optimal in the spherical isoparametric inequality, right? This right-hand side must be close to 0. Then also the left-hand side must be close to 0 by this inequality, and which means that up to a set of small measure, the set E is very close to a metric ball, which is a spherical cup. And the proof is along the same lines of the Cicalese and the Leonardi selection principle. All right, so this is about question 2 in the Euclidean and in the spherical setting. So the Euclidean and the spherical and the sphere are very special manifolds. Basically, they are the manifold with the highest possible degree of symmetry. And the Euclidean and the spherical isoparametric inequality are for a fixed space, are for the round sphere or for the Euclidean space. Instead, the Levigram of inequality is quite different in nature, because it is not for a fixed space, it is for any manifold with reachable below by n-1. So we have not a fixed space, and such a manifold may have no symmetry. You can take any manifold with lower bound, with such lower bound on the reach. And the above approaches seem not to be applicable. So the symmetrization approach by Fusco, Maggi, and Patelli doesn't look say to have chances here, because basically what is the symmetrization is usually you are in a very symmetric space like Rn or the sphere, and basically you want to replace, you cut your set E in slices, and then you want to replace each slice by a symmetric slice with the same volume. Okay, so you symmetrize your space by moving slices in your ambient space using the symmetry of your spaces and replacing each piece with a more symmetric piece. But you need to move these kind of pieces with the isometric group of the ambient space, and you can do that in Rn or in Sn, but maybe your manifold M with lower bound on the reach has no symmetry at all, and you cannot move anything. Okay. The approach via Bragnier map, say with the two optimal transport, one of Figalli, Maggi, and Pratelli, works very well in the Euclidean space, but already in the round sphere is an open problem to prove the spherical isoparametric inequality without any stability using the Bragnier map. So it is even more challenging to study the Levigram of inequality with such an approach. And regarding the selection principle, this is probably the most flexible approach, but it doesn't seem to be applicable in this setting because it works very well with smooth convergence. So it would work. It may work if one has smooth convergence of metrics, but when you work in the realm of manifold with lower bound on the Ricci curvature, the natural notion of convergence is a measure of Hausdorff, which is even weaker than C0 convergence. So it is very hard to have better convergence than Gromov-Hausdorff in this setting. And so it is hard to apply this selection principle. Okay, so what we do instead, so in order to attack this problem, we work with the L1 optimal transport and with the so-called localization technique. So let me give you a brief history of the localization and what it entails. So the localization technique is a way to reduce an a priori complicated high-dimensional problem to a family of simpler one-dimensional problems. So basically, you do a dimensional reduction of your problem until you have one-dimensional problems that you can treat quite explicitly. Okay, so how this dimensional reduction is done? So usually, when your ambient space is the Euclidean is Rn or Sn, then using the high symmetry of the space, such a localization is obtained usually via iterative bisections. So you bisect countably many times, and after bisecting countably many times, you see that you reduce the dimension by 1, and you keep bisecting countably many times until you reduce by 1 further dimension, and until you have something of dimension 1. This is the rough idea. And the roots of these ideas, of this technique, go back to a paper of Pan and Weinberger in the 60s, where they prove sharp estimates on the first eigenvalue of the Neumann Laplacian on compact convex subsets of Rn. Then it was formalized as a technique by Gromov, Vitali Milman, and by Kannan, Lovatz, and Simonovitz, but still in spaces with very high degree of symmetry, Rn, Sn, Hilbert spaces, by using bisections. And then there was a breakthrough by Boas-Klartag in 2014, who was able to extend such a technique to Riemannian manifolds with lower bound on the Ricci curvature using L1 optimal transport. So the big advantage of the approach proposed by Klartag is that no symmetry is assumed. So this L1 optimal transport works very well without any symmetry of the space. But this approach still was heavily using the smoothness of the space, because basically it was doing estimates on second fundamental form of level sets of countable potentials, and which uses smoothness. So together with Cavalletti, we extended this L1 optimal transport approach to localization to possibly non-smooth spaces with lower bounds on the Ricci in a synthetic sense via optimal transport. Okay, so with such a technique, together with Cavalletti and Maggi, we proved the quantitative Diagram of inequality, which says the following. Fix some volume V between 0 and 1, a dimension n. Sorry. Then there exists a constant which depends on the dimension and on the volume, so on n and on v, with the following properties. Let Mn be an n-dimensional manifold with the Ricci band below by n-1. Then for every subset E of M with the renormalized volume equal to V, there exists a metric ball inside the manifold, so a metric ball B inside the manifold M, having the same volume as E, and such that one can control the volume of the symmetric difference between E and such a metric ball with the constant times the deficit in the Diagram of inequality. So here we are taking the difference between the renormalized perimeter of E and the isoparametric profile of the sphere to a suitable power. In particular, if that E is an isoparametric subset, so if the perimeter of E is exactly the isoparametric profile function of the manifold at the volume V, then one can bound the symmetric difference between the subsets, such an isoparametric subset, and a metric ball with the difference between the isoparametric profile function of the manifold and the one of the sphere at the relevant volume to the right power. Okay. Now let me remark a key difference between the quantitative Euclidean isoparametric inequality by Fuchs, and Fratelli, or the quantitative spherical isoparametric inequality with our result. So in the quantitative Euclidean isoparametric inequality, one was taking a subset E inside inside Rn, was comparing the perimeter of such a subset with the perimeter of the ball inside Rn, so in the same space. Okay. If this was small, then the subset was close to the metric ball in L1 sense. Okay. Here we're doing something different. So here what we are doing is we are taking the normalized perimeter of the subset inside, and this subset is a subset of M. Okay. And what we are doing, we are comparing it with the isoperimetric profile, not of the manifold, but of the sphere, because this is the comparison in the Levigram of inequality. So we compare it with the isoperimetric profile function of the sphere at the relevant volume. Okay. And if this is small, then the set must be close in volume sense to a metric ball, not of the sphere, but of the manifold M. So this ball here is inside the manifold M. Okay. So here there is an interplay between things which happen in the manifold M and things which happen in the sphere. Okay. So this left-hand side is completely inside the manifold. This right-hand side has one part which is happening in the manifold and one part which is happening on the sphere, on the model space. And say a challenge is to make the manifold speak with the sphere in order to have such inequality. And the idea for using it, for having this dialogue between the manifold and the sphere, is to use optimal transport. Okay, so I see that time is running out. So I will skip a part and I will go directly to give you some ideas of the proofs. So before giving you some ideas of the proofs, let me just say that the results that I presented so far, so theorem 1 was the one of Berard-Besson-Gallot, so the one that was saying that the diameter was that if the Levigram of inequality, if the equality in the Levigram of inequality was almost attained, then the diameter was almost pi. Okay, and theorem 2 is the one that I just stated, that if the equality is almost attained, then the set is close to metric ball. Okay, I stated them for smooth Riemann manifolds with reachable below by n-1, but actually we proved this, both results much more generally for possibly non-smooth spaces with lower bound on the Ricci curvature. And these are the so-called CD spaces by Loch, Sturm, Villani. These are metric measure spaces, so metric spaces endowed with a reference measure, playing the role of volume measure. And these are a priori non-smooth spaces of dimension at most n, and Ricci but below by n-1. But now Ricci is not anymore a linear form as in the smooth setting, and both bounds must be interpreted in a synthetic sense via optimal transport. So basically, you consider convexity properties of shootable entropy functionals in the Wallenstein space of probability measures, endowed with the topology by L2 optimal transport. And this is the approach by Loch, Sturm, and Villani. Okay, so I don't have time to enter into this topic. Let me just give you some examples that enter into this very general framework. So not just smooth manifolds with H bounded below, but also weighted manifolds, meaning Riemann manifolds endowed with a weight. So you are multiplying the volume by a smooth weight and having n-dimensional Bakry-Emery Ricci tensor bounded below by n-1 are in this framework. Then if you take a Gromov-Hausdorff limit of Riemann manifold with lower bound on the Ricci, then these possibly non-smooth limits called the Ricci limit spaces are entering into this framework. Then also finite dimensional Alexander spaces with Ricci curvature bounding from below by 1, with the sectional curvature bounding below by 1. So these are metric spaces with the sectional curvature bounding below by 1 in the sense of channel comparison a la Topogonov. And even thin structures enter into this setting. finite structure with suitable, say, with strictly convex norm on the tangent spaces. Okay, so this framework is very, very general. It allows this kind. It allows singularities. It allows even non-Riemannian structures like finite structures, and it is closed. And it allows also taking limits, or possibly non-smooth limits, of Riemannian manifolds. Okay. So I don't have time for this part 2. Let me just give you one idea before I end. So what is the key idea for these proofs? So what is this one-dimensional localization? So this localization means to have a good partition of your space X into one-dimensional pieces. So basically, we have a metric measure space XDM. So it is a metric space with a measure, and a one-dimensional localization is a partition of the space into geodesics, such that with some special properties. So the first property is that that this family X alpha. So alpha is the index, Q is the set of the indices. It's nothing to do with the rational numbers. It is just a set of indices Q. We have that it is essentially a partition in the sense that they are all disjoint and they cover X up to a set of measure 0. Then the second property is that one has an associated partition of the measure, which is called disintegration of the measure, meaning that one can find a probability measure on the set of indices. So this Q is a probability measure on the set of indices. And one can find for every element of the partition X alpha, one can find a measure M alpha, which is concentrated on X alpha and is a probability measure on it, and such that the volume measure M can be written as integral of the one-dimensional measures M alpha times the measure Q. And you can think of it as a kind of non-straight Fubini theorem. The third property is that each X alpha is a geodesic in the space X. And key thing, if we consider X alpha with the measure M alpha, it has, in the sense of Buckley-Emery Ricci curvature, it is a weighted segment. It is a segment with a weighted measure. I want that to have the same lower bound on the Ricci as the ambient space. Okay. And the fourth property is that how these measures M alpha are talking with the set E. Well, each of the the elements of the partition X alpha is intersecting the set E in a subset with the same volume. So all the intersections have the same volume, and is the volume of E. Okay. And how to obtain this localization is to consider the optimal transport problem with the cost given by the distance between the characteristic measure of the set to its complementary. Okay, so you have the set E, and you're doing the L1 optimal transport between E and its complementary. And such curves X alpha correspond to the gradient lines of the Kantorovich potential. So and which correspond to the geodesics that you are using for doing such an optimal transport. Okay. Now the last one is the next one is the last slide. So now let me tell you just how to use such four properties to prove the Lévy-Diagram of inequality, and then I don't have time to tell you how to quantify that. But believe me, that then you can quantify it. Okay. Now let's see how to prove the Lévy-Diagram of inequality. Okay. So we have the total mass is equal to 1. So this measure M corresponds to the renormalized volume measure. This is why we consider always the measure of the set divided by the measure of the space M. Okay, so we have our so the renormalized measure of the set E is between 0 and 1. We take no, this is how to construct the localization, and I want to skip it. Time for that. So it's the Lévy-Diagram of inequality. Okay. So we want to find a lower bound on the boundary measure of E. So one way of talking about the boundary measure of the boundary of E is the atomic content, which is this right-hand side. So which is the volume of the epsilon enlargement of E. So we take all the points at distance at most epsilon from E, minus the volume of E divided by epsilon. So this is basically you are taking the volume of the epsilon to Bragg neighborhood of E, and you divide by epsilon, and you let epsilon go to 0. And this is roughly, if E is a smooth subset inside Rn, you converge to the boundary measure of the set. Okay. All right. Now we use that we have this partition of the measure M by saying that the volume that such a measure M can be written as integral over Q of the measures M alpha. Okay. So we just replace M with the M alpha integrated with Q here and here. Okay. Now I have the liminf inside, and I can put the liminf, I can bring the liminf inside with the Fatou's lemma going lower. So the Fatou lemma tells me that I can bring the liminf inside having the lower bound. This is fine because in the isoparametric inequality I want to find a lower bound on the volume on the perimeter. So on the boundary measure. So I'm still happy if I go down. Okay, and then I know that each of the measures M alpha are concentrated on the geodesic X alpha. So I don't lose and don't gain anything if I intersect with X alpha here. All right. Now I observe that if I first intersect with X alpha and then I enlarge and I intersect again with X alpha, well, this set is contained in the set that is obtained by first enlarging by epsilon and then intersecting by X alpha. This is just a one line of exercise in set theory. And so this set here is contained in this set here. And so if I replace this with that, I go down and I have an inequality. And then I copy that. Okay. Now I observe that what I have inside this liminf, so this guy here, is exactly the analog of that for the measure M alpha. So this is this liminf is exactly the atomic content of E intersected with X alpha. Okay, so here is exactly what I was saying before, that with this localization you can reduce the proof of an inequality by a family of one-dimensional inequalities. So here you started by an inequality, you want to prove a lower bound on the atomic content of E, and what you reduce is to find a lower bound on these one-dimensional guys. So these guys are measures on segments. So you want to find a lower bound for this family of one-dimensional guys. Okay, but now this is easy because each M alpha is a CDKN measure on the segment. So by the smooth diagram of inequality for weighted measures, one can bound from below this by the isoparametric profile function of the sphere at the measure M alpha of interacting with X alpha. Now I observe that the intersection of E with X alpha have all the same volume with respect to M alpha, and it's the volume of E, and this was property 4 before. All right, but now this does not depend anymore on alpha. Q was a probability measure, so I can take it out, and putting all together, we have a lower bound on the boundary measure of E with the isoparametric profile function of the sphere, which is the diagram of inequality. Now, in order to prove the stability, one needs to check what happens when the equality is almost achieved, and this requires quite some work, and I don't have time for doing it. So thank you very much for your attention, and if you have some questions, I will be happy to discuss it.
Okay, thank you, Andrea, for such a wonderful talk. I think we have time for 1 or 2 questions. Well, as a matter, okay, it's open. As a matter of fact, I do have a question, and I think was actually a slide you skipped over your presentation, because as your presentation went on, I was thinking what was so special about L1 transport theory for this, for this to work. And can you say something about it? I mean, could I make it work on that, let's say, in L2 construct? Is an L2 transportation theory, or why not? And what?
Right. Yeah. Thanks for this question. It's something that I wanted to say, but I didn't have time. So thank you for asking it. So let me tell you what is one. Let me tell you first what is say quickly what is L1 transport and L2 transport and what are the differences. So what we do with L1 optimal transport, you consider the measure you want to do optimal transport from the set E to its complement. Okay. What does it mean to do L1 optimal transport? It means that you take as mu0 the characteristic measure of the set normalized to be a probability measure, and as a final measure the characteristic measure of the complementary normalized so that it becomes a probability measure. And the L1 optimal transport problem corresponds to taking the infimum among all the possible probability measures on the product x times x, such that the push forward on the first coordinate is the first measure, and the push forward on the second coordinate is the second measure, mu1. Okay, and take the infimum of what? You take the infimum of the integral of the distance function among all these possible transports. So each gamma corresponds to a transport, and you take the infimum of this cost, the distance, with respect to all the possible transports from mu0 to mu1. Now, by using optimal transport techniques, you can see the book of Villani, for instance, there exists a minimizer, gamma. This is not hard because this is a convex problem. So you have a minimizer, which is a probability measure in x times x. And more interestingly, there is a one-Lipschitz function, phi, from x to r, which is called counter-Lorentz potential, which is telling you where gamma lives. So it is telling you that if you consider the set of pairs, so this capital gamma are those pairs in x times x, which saturate the one Lipschitz condition on the counter-Lorentz potential. So are the pairs such that phi of x minus phi of y is equal to distance x y. So these are pairs in x times x, and what you know from optimal transport is that the measure gamma, which is minimizing the optimal transport problem, well, this is concentrated on this set of pairs capital gamma. And why is it interesting? Well, because now this capital gamma is a subset of pairs, and you can use it to define a relation. So you can say that 2 points are x is in relation with y if the pair xy is in gamma, or switched if yx is in capital gamma. And the interesting thing is that this is easy to check by triangle inequality and using the one Lipschitz condition, that such a relation is an equivalence relation on X, and the equivalence classes are geodesics. Okay, so just using optimal transport, you get a partition of the space X into geodesics, and such a partition is really driven by X, is really driven by the set E, because you are doing optimal transport from E to its complement. All right, and here it is key that you are using the distance. Otherwise, with the distance squared, you wouldn't. This proof wouldn't work. And what happens with the distance squared, that the geodesics can actually cross. So this is probably in the next slide, right? So when you consider instead the L2 optimal transport, that probably is more standard for people having read, say, surveys on optimal transport. So in the L2 optimal transport, instead of taking the inf of the distance of the integral of the distance among all the possible transport, you take the infimum of the distance squared. Okay, so this is still very nice, and it is very nice in particular because it is inducing a map. However, what happens is that even if you have a map which tells you where to go at the final time and also at intermediate times, it may happen that the geodesics which are performing the transport may cross at some intermediate time. So at some time, say, so you have a geodesic at some parameter s, the other one at some parameter t, they can cross, which is saying that the L2 transport is not inducing an equivalence relation. And for the proof to work, it is really key that we have an equivalence relation. The L1 optimal transport does induce an equivalence relation, and so that's why it is better to work with that for this specific problem.
Yeah, quite interesting. All right, thank you, Andrea. So let me ask if there's any other questions, comments. Well, final chance. Very okay. So if there are no more questions, let's thank once again Professor Mondino for this very nice talk, very interesting talk. And I'll move back to Professor Rincon to continue the session. Thank you, Professor Andrea, for a very nice talk, and thank you, and thank all the audience for being this talk. So
thank you for your attention. Thank you very much. My pleasure. Yeah.
Thank you, Andrea, for excellent talk. Now the next talk is